And thank you guys for joining us today. Really excited to be chatting through this. So let's start off with kind of just orienting ourselves with a few instruments that maybe a lot of people are familiar with, and obviously we can kind of talk through different tools in Q&A. But I like to think about where we sit in the marketplace and these two axes to start with, and that's resolution. So what's the smallest feature you can see versus the detection limit? What is the smallest peak you can see? So going from, on the y-axis, parts per billion level sensitivity, all the way up to weight percent level, or your major elements. And we kind of have two end members that we can think about here. On the left side, we have SEM-EDS, which a lot of you are probably familiar with. And this is a electron beam tool where we can look at things in the nanometer scale, right? We are looking at things very small features. We're seeing a lot of, interesting morphology, making all these beautiful images we're used to looking at. But when it comes to actually doing the chemistry, we're really only able to look at weight percent level things semi-quantitatively. And the other dimension here is not all of the elements. There are limits to what these techniques can show you from, let's say, lithium to uranium, right? If we're thinking about, the periodic table and all of the masses there. On the other side of that extreme, we have ICP-MS. This is where we might take something like a piece of metal or a rock, and we're going to digest it in some acid. We're going to do some chemistry to it. Then we're going to put it through a plasma and do mass spectrometry. The advantage here is that, as you can see on the y-axis, we get very low limits of detection. It's a very quantitative technique. But again, you're taking grams of material and digesting it. You need acid labs. You need a lot of argon or helium gas supplies, or now some nitrogen gas supplies. You basically have a lot of consumables. You need clean lab. It's a lot of overhead. And you're only able to look at one data point, generally speaking. You get a point of data for whatever it is. Doesn't show you where your chemistry is, like what SEM-EDS is doing. So the Massbox, we sit right in between here. So where we sit is we're never going to be able to go look at something at 1 nanometer resolution. We have a spot size that can move from about 1 micron up to 150 microns, right? And so we can go to small scale to a relatively large single spot scale, but we can move that over a 90 millimeter by 90 millimeter area. So we'll talk more about that later. And when Ellen goes into application. So about 3 inches by 3 inches. We can tell you your chemistry in space that's at a much larger resolution while still being able to provide average data values of what an ICP-MS can give you too. So on the spatial resolution side, we can get high resolution images, give you context for your chemistry, and we can do that to very low limits of detection. We're talking, 100 parts per billion or lower for a lot of elements. Now, obviously, there is some caveats to that, but in general, that's how you can think about, if you want very low limits of detection of lithium, we're an amazing tool for that, right? Same thing for all of the lanthanide elements that are difficult to do by other techniques. All of these elements, low limits of detection, high spatial resolution. And it's not just high spatial resolution. What we tend to find is that this is a really useful spatial resolution for a lot of our industry customers that want to do chemistry for process control, quality control, or anything else in between. So let me talk a little bit about how this works. So what are we actually doing inside of this box? I'm sure a lot of you are familiar, but this is a 2-laser process. First, we do ultra-fast laser ablation. So we bring in a 213 nanometer laser. We're ablating material. We're really focused on trying to make a stoichiometric neutral particle cloud. So we want the particles in the cloud to look like the solid that we ablated it from, right? And then we're going to take in another laser and we're going to saturate that cloud. And we're going to rip off an electron, turn it into an ion, and we're going to go right into a mass spectrometer from there. And the advantage to that is we get all of the elements, because we're saturating that whole plume at every single laser shot. So you can analyze your whole sample. And let's say that, with a quadrupole ICP-MS or a magnetic sector, you're going to have to ask it what you want to look at. I want to look at manganese, nickel, iron, all of these elements. With our technique, it's fully indiscriminate. We're going to give you every element, whether you like it or not. And this is amazing because a lot of times customers will send us samples and they'll say, I really care about these 5 elements. We say, okay, no problem. We'll quantitate those for you. By the way, did you know you have a lot of tungsten? Like, no, we don't have a lot of tungsten. I was like, have you ever looked for tungsten? Like, no, I guess we haven't. Well, it turns out you have a lot of tungsten because you never thought to ask if you did before. We give you everything in the system because of how we designed it from the ground up. So ablation, ionization, time of flight, mass spectrometry. So the advantages here are we can analyze anything solid and flat. It's in a vacuum environment, so we don't have gas flows in order to have a requirement for noble gases. All vacuum, we can deal with air-free transfer vessels. So for reactive materials, that's no problem for us. It's very clean mass spectra, so we are able to really look at the isotopic fingerprint, which we'll show you some examples later, and confirm that that actually is lead because, well, there are all the isotopes of lead, right? As opposed to trying to pick out which isotope we should use because we have all these interferences to deal with. We don't have that limitation like a lot of other techniques. And like I mentioned, we have the full mass spectrum. And we don't have to do specific tunings for different elements or for different materials because this is a very static system is the way to think about it. All of the electric fields are just DC voltages. We don't have a lot of RF devices or gas flows, like I mentioned. So this makes it a very stable instrument over time, really allowing it to be well used in industry where you want the same data day in, day out. So where we find ourselves fitting of like where are modalities of operation here, there's three major ones that we like to think of. One, I briefly talked about, we have this full periodic table, especially those elements like lithium to fluorine that are very difficult to measure by other techniques, or in some cases, like the lanthanides are also difficult to measure by tools like LIBS or something. We can get this entire periodic tables worth of analysis at every spot, and we could do so quantitatively. And the reason we can do that is because of how we produce our neutral plume, how we ionize it, and how we transfer it to a mass spec. There's nothing in between, allowing us to be very linear, very quantitative across the periodic table. The other thing that we talked about that we can do is we can put your chemistry in context. We can do elemental mapping. So every single pixel on these images that you see have a full mass spectrum. We can just turn on different elements. So what you're looking at here is this is a rock, right? So rocks are a total mess when it comes to chemistry. And at every single pixel, we can say, where's the sodium? Where's the potassium, the manganese, or the yttrium? Whereas you might be able to look at this on something like a test scan or an SEM, and you're going to be able to do mineralogy for sure very well because you're looking at the weight percent levels, but you're not going to be able to look at those trace elements like the manganese and yttrium that might be in there that give a lot of important information, or especially at an ore, you might be looking at something down to the parts per million level, and you want to know what phase those are in. So we have a lot of examples of doing things like gold analysis, for example. And then if we take this map, because we are removing a little bit of material on the order of tens of nanometers per laser shot, we can just keep doing it and then make a 3D reconstruction of where that chemistry is as well. This is one of the classic examples that we do in the industry space on this side is in batteries. So reconstructing the chemistry of an anode. So what you're actually looking at here is an anode where the green is the lithium and the orange is the copper. And not only were we able to look at the distribution of lithium in space here, of where's the lithium, but what contaminants were there? What did the SEI layer look like? All of these sorts of questions that the researchers or industry professionals could never ask before. We can now answer these. And we did it in a vacuum environment, so we didn't have to worry about the lithium catching on fire, which is always a plus. So what I want to talk about next is just a quick intro of some of the improvements we've made. Obviously, like Ellen mentioned, the box is still as sexy as ever, just in a different shape. We really wanted to focus on, some ergonomic improvements as well in the lab space. We know bench space is a premium. And so we kind of changed the layout of this, made it easier to both load samples, to interact with the touchscreen, and in order to really optimize for high throughput environments. There's a lot of stuff we could talk about on the automation side that's baked into the entire UI or the entire experience of the system. But we also made a lot of changes to how we're handling the samples, how we are analyzing them, what type of mass spec we're using, all these sorts of things. So to start with, we made a open format sample holder. So this is just one example where we're holding a lot of different gemstones here, which are regular objects. And this can be fully customized for anything a customer needs. So if you always handle something that's 10 millimeters, 5 millimeters, 30 millimeters, irregular, whatever it is, that's part of our process where we have a concierge service of understanding what you need to analyze, how often you need to analyze, and what you're looking for. And that starts with how do we hold your samples. So within this volume that you see, which is about 90 millimeters by 90 millimeters by about an inch, we can create any custom holding solution. And what we've done differently here is we have gotten rid of an entire axis. So there's no height adjustability. All of the samples are brought to one surface. And that way we can guarantee that you are getting the exact same laser power at any part of the top of any sample. So really simplifies the entire workflow on that. Then once you go to put your sample in, if any of you are familiar, we used to have a chamber door that would open. It would take about 10 minutes to pump down before. Now with this new Airlock system, we're able to pump down in less than a minute. So we can take that sample holder on the left, you reach in, you put it down, Airlock lid comes over, and in under a minute, you're pumped down, ready to analyze. This has obvious advantages for automated routines, robotic handling, a ton of applications like that, which again, we're happy to talk about that kind of concierge service that we provide when it goes to not only selling you a tool, but making sure that it integrates directly into your environment. And we made a lot of improvements on the hardware. We can now look down to, like I mentioned before, lower than 100 parts per billion for a lot of things. So what you're looking at is a proper isotope pattern for lead that's at a known concentration of 300 parts per billion. And you can see all of these peaks are well over background. We're really pushing detection limits here. So this is allowing us to push into a lot of spaces for quality control of high purity materials, contaminants that matter, or being really confident for certain ores where maybe 1 ppm makes it economically viable and you want to have a confidence interval of over a factor of 100. We can achieve that now with a lot of the changes that we've done on the hardware by vertically integrating. And ultimately, by making those choices, we've made it more reliable as well. So last thing, or maybe second to last thing that I'll touch on here, is all of that translates as well to very linear, quantifiable data as well. So this is just a quick test where we took a bunch of different types of steels. So if any of you are familiar with steels, steels can have a huge range of composition. So the bottom right graph is a good indicator here. You can go from parts per million levels of nickel all the way up to 20 weight percent nickel. And those are all very different grades and very different matrices, even within that steel family. And we're able to maintain linear calibration across those very easily and quickly. So we can make this calibration curve, put it in, and have a high confidence of quantitating anything within this dynamic range, which is very wide. And again, going down to very low limits of detection. You can see down in that vanadium plot, we're into the single digits parts per million over there, all the way up to almost half a weight percent.